Okay, hello everyone. Good afternoon. Welcome to ELC. So my name is Karthik Poduval. I'm a principal software development engineer at Amazon Lab126. Today I'm going to be talking about V4L2 media controller request API, and it's a very long name. So this is last year at the same conference I had spoken about media controller for ISPs, and this was one part I had not covered there, so I thought I'll do a separate session for it, exclusively talking about the media controller request API. So I'll begin with the first question is what's the need for such a request API, right? So for those of you who are familiar with V4L2, like V4L2 has this thing called V4L2 control, which is the default mechanism to set parameters to your video device or sub-device. So it could be applied to, in a media graph, you might have many participating video devices and video sub-devices, and you can use V4L control to set parameters to them or get parameters, right? You could do both of them. And there are various types of controls. It's pretty exhaustive coverage-wise. The thing about V4L2 control in its default form is asynchronous in design. So you can do a set control. It can be called at any time, and a get control can be called at any time, right? So some of the problem with this is that it's very hard to time a set control and a get control to a specific frame, right? Sometimes you need to do that because, especially if it's a volatile control, it's always changing values. You need to capture it at a specific amount of, as a specific time period. Very true for ISPs and, time-based streaming hardware devices. So for these reasons, since you cannot do that naturally, unless you use request API, you cannot use a straight V4L control to be used as metadata. It's very difficult. And you can't even use it to apply setting to a specific frame. So per frame settings are also very hard to do with the V4L2 as is. So some of the other needs that drove the design for the request API are, we have the decoders, V4L2 mem-to-mem decoders. So I think there's a recent trend where a lot of the decoders are turning stateless. So I think in the past, a lot of ARM-based SoCs used to have stateful decoders, which means that you read the file contents and give it to it, and a lot of the internal state management was being done either by the hardware or by some accompanying processor. So that is changing now, and a lot of the decoders are becoming stateless. So with that, what happens is that the state maintenance is now moved to user space. So typically what happens is that user space will parse bit streams, and there's a need to now set parameter on a per frame basis, or probably even get per frame metadata, because that's kind of a part of the closed loop of the user space parsing of the state. So there are high-level decoding libraries. The ones I could find are Vulkan video extensions, this Intel VAAPI, and GStreamer. So these software frameworks on the user space are capable of doing state parsing in user space. But in order for this to work with hardware that is stateless, there is a need for drivers to be able to either do per frame settings or receive per frame metadata. And here are a few examples of some controls that may need to be adjusted like this. So one of them is to set bit rate, and SPS and PPS are something related to H.264. Pardon me, I'm not an expert on codecs, but it falls under this, so I did some of my own research and talked to my colleagues to get some information about it. But there are many others. I just listed a few which made the most sense. So these parameters or controls may be applicable or relevant to a given frame only. So you might need to set them on a given frame boundary and then see the metadata and then change them on the very next frame. So this totally depends on the content of the file and what kind of, what the user space decides. So it's pretty interactive. So the other need for request API comes from complex camera ISP pipelines. So this is the area I'm more familiar with. So in case of cameras, you could always benefit from per frame metadata. I mean, there's no application which will tell that it does not like to know what is the exposure for the given frame, or gain for the given frame, or in some cases, what was the crop. If you have a dynamic crop enabled in your ISP, you might like to know what was the crop parameter applied to this frame. It's especially more helpful if you're going to pass that frame for further post-processing, so you should know what crop was applied to that frame. Sometimes the 3 algorithms can benefit from both of this, right? So if you know what was the current exposure applied to this frame, it could wait. If it just applied something and it's not really shown up, so 3 algorithms can wait till the metadata says that the previous exposure or gain has been applied. So metadata is extremely helpful to camera ISP pipelines, and that's one of the needs for having a request API. So the other use for request API is in the computational photography use case, right? So some examples here is like HDR framing, where you do 2 back-to-back captures, one with high exposure and low exposure. And then in software, you could use them to combine them to create a high dynamic range image. So in order to do that, you'd have to, apply a per frame setting for high exposure, another per frame setting for low exposure, and via metadata, you track when you get those frames back and use them to combine them to form an HDR, high dynamic range image. Another use case is multifocal point capture. I think some smartphones do this. So they'll just move the lens voice coil motor, which is the hardware that assists with autofocus or manual focus, and they'll move it across various steps and make multiple captures. And sometimes you need to know what was the focal length of each of those captures via metadata, and then you can use that to do like depth field images or something of that sort, right? So the other is burst capture with varying frame ISP settings on each. So that's a fictional use case, but yeah, something like that could also be done with per frame settings. So largely speaking, these are some of the requirements that drove the need for a media request API. So now with that, we now know what kinds of applications are using V4L2. There's the codec side. There's ISP. There's also another class of devices which I don't have a slide about, which is V4L2 mem-to-mem post-processor devices. So they are not codecs, but they do use the V4L2 mem-to-mem framework. Those devices can also benefit from request API. So I can provide a very simple example. So if you have a hardware post-processor that actually has a volatile register that updates at the end of the frame, and you need to send that as metadata, I think request API is perfect for that. If you try to time that with a V4L get control from user space, it's probably going to be extremely hard to get the right value because it's volatile by nature, right? So you need to time it at exactly when the DMA completes. So those sorts of things. And if you had a requirement to set some setting before doing the post-processing, so you could use the per frame settings. So these are kind of the needs that drove the creation of the media request API. So Media Controller Request API is designed to allow V4L2 to support devices such as stateless codecs, complex camera, ISP pipelines, as well as other V4L2 mem-to-mem devices, which also use the same V4L2 mem-to-mem framework. So it brings in the following concepts, right? Now, it's the same S control and G control, but using slightly different mechanisms. You can use them to do per frame settings using the VID IOC S control, and per frame metadata, which will use the VID IOC G control. So without request API, let's just say such an API didn't exist, what would you have to do? You would have to flush the media pipeline, because to be sure that your per frame setting is applied, you need to restart, right? That's the only way to 100% make sure. So that'll lead to some wastage of probably added latency, more time, increased power, all of those things, right? So you'll have to then reconfigure the settings with the new frame, and then you got to wait till the frame arrives for the new setting, right? So this is the only way to be 100% sure that you are able to get per frame settings and receive per frame metadata. But that's what will change with the media request, with the controller request API. So let's go over the basics, right? So how does, on a high level, how does it work, right? So because the request can be complex, right? There could be multiple devices on a media pipeline that might participate in this request. Hence, the idea of request is actually tied to the media device and not the individual parts that contain it within it. So the way it works is you allocate a media request on a media node. So there's a dev node that gets created for every media device, which is a device file /dev/media some number. And so there is an IOCTL to allocate media request using that. I will be covering the API in a later slide. So once that is done, you will get a file descriptor. That's what the allocate API does. It provides you a file descriptor. Then you need to make the control calls on that file descriptor. So for your per frame settings, you do S control, and for your per frame metadata, you do a G control. But you have to operate it on that file descriptor. Rest of the API looks the same, and there's an example coming up in the future slides. After this, you need to queue this media request that you allocated using the first step along with the video buffer. So you normally tie this to a specific video buffer or one of the video ports of your complex ISP. In case of codecs, there's only one, so it's a little bit simpler, but for ISP, there could be multiple. So you need to decide which one, or you could do it to potentially all of them. And you have to queue this media request along with that video buffer. So the media driver is going to make sure that the per frame setting as well as the per frame metadata are not timed, because the driver has, along with the hardware, they have the knowledge on when to apply the per frame settings and when to get the per frame metadata. So that functionality is now moved into the driver. And once the buffer is returned, right, normally after the hardware produces the buffer, through the driver, the buffer will be returned to user space. So once the buffer is returned, if you did queue this buffer with a media request, you need to wait for that media request also to complete. There is another API. I think it's basically like a poll call on the file descriptor. And once that happens, then you can query the controls using the G control API, and then that's going to get you all the per frame metadata. So I do have some diagrammatic representation of this. So first we need to understand the relationship between all of this, right? So there's a media device. Using media device, you'll allocate a media request. Media request is basically an FD, it's a file descriptor. You associate that with a control. You also associate that with the video buffer, right? And these video buffers are typically allocated by the video device, or they're allocated elsewhere and imported by the video device. So this is sort of good to understand. So let's take a look at an example, right? So over here, what we see is simple media device. This contains one video device, very true for stateless codecs. So using the media device, you'll allocate a request. So the orange box here is the request object. And you're going to allocate a buffer using the video device, right? Typically, there'll be like a pool of these. For simplicity reasons, I'm just showing one, but there's going to be a pool of buffers, right? And you're going to, at a given point, in my mind, a simple association is for every video buffer, you have a matching media request. It makes it simpler, but you don't have to do it that way. That in my mind is a very simple way to handle this. So once you've done this, right, you grab the FD and you do all of those things, right? So once you have the FD of the request, you can set control on that request object using the standard V4L2 control API, nothing different. It has been extended to point to a request FD if requests are present. And there's some flags to indicate that you're using this as a part of the request API. It will be covered later. And then once that is done, the next thing to do is to queue the request and queue the buffer separately. You got to do that. So once you do that, now the request object as well as the buffer have moved from user space into kernel space, right? So at this point, the video device actually knows when to, apply the per frame settings and when to get the per frame metadata. So it's going to issue these callbacks. And once that happens, the next thing to do is you dequeue the request and you dequeue the buffer. And that has happened. Now the video buffer as well as the request has gone back into user space. So once it's in user space, now you can do your get control. So that becomes your metadata, right? So this is basically the diagrammatic representation of how your application programming would look. We can also take a look at the API. So over here, you'll have a V4L2 buffer, you'll have a control, extended controls object, and then you have a request FD, right? First, you do an ioctl using the media file descriptor. This is the media device file descriptor, like I mentioned earlier, /dev/media some number. So you need to make this ioctl and pass in the request FD local variable here. So then that's going to get populated with your file descriptor for the request. And there's some hidden code here, and then after which, that's basically showing that you set some controls, whatever it has to be, right? But then there's a controls has a which field in that you're going to say that you are going to use this for request API, and you're also going to pass in the request FD number to here, and then this is the standard ioctl call for making S controls. So you just do S's, right? The difference here is that if you didn't do these two steps, that control would get applied immediately. But because you put these two steps over here, right, you're now letting the driver decide when to set that, and it would do it as appropriate for that particular hardware, right? Maybe before a frame starts. Once you did that, the next thing to do is to queue the buffer, right? So as I remember we mentioned earlier, right, the request is also tied to the V4L2 buffer. So over here, you're going to tell that it's video output. Now, I'd like to just spend 1 minute talking about this. So for V4L2 mem-to-mem devices, the requests can only be set on the output side, not on the capture side. But for ISP and camera kind of devices, you can set it on the capture side. So this is a strict restriction which exists as of now. That's why, and this example is for a mem-to-mem device. So you need to set it to the output. And there's again a buffer flag that indicates that, along with this buffer, we are also going to be queuing a request file descriptor. So that's kind of shown over here. And then you do a regular QBuff. This is exactly the regular API do for the QBuff. The additional steps here are these two, the flags and the request FD. Going to the next slide. So now, like I mentioned earlier from the slides we saw, like we need to also queue in the request. So you queued the buffer, you pass the request FD to it. You need to now queue the request FD itself. So there is a media request IOC queue for that. So you need to do that. And so this is the example shown for the capture devices, very similar to the previous, but actually, yeah, sorry. No, I'm mixing up. This is still for the mem-to-mem devices. The capture is where you get back your, the content, right? So you do a dequeue buff, and then after that there's a step here to wait for the media request to complete. So that's just a PAL call here, and then once you've done that, then you just do a G control call. So that's how you get your metadata. So this is a generic V4L2 mem-to-mem example, which is not from the, which is not a codec, right? So here what you would do is you on the output queue, you take a request and a buffer and put it in, and on the capture queue, you get back the buffer, right? So that's a simple example here. If you were to do this for a codec, right? So there is a user space. There's three possible options here: Vulkan Video, there's the Intel VA API, and GStreamer. So these user space components would do the parsing of the decoding and the parsing of the codec data, and they would basically, they're aware of the request API, so they would make these per frame settings and rely on the per frame metadata to make per frame adjustments. And just like before, request and the buffer would get queued to the output side, right? And then you get it back on the capture side, right? So let's take a look at the complex camera use case. So in here, like I said, it can work for the capture because an ISP is a capture device, it's not an output device. So you would apply your per frame settings and you receive the per frame metadata. And I've just shown the user space here, which these days tends to be lib camera. And yeah, I just put this disclaimer here because I think though it is designed for V4L2 mem-to-mem and capture devices, by default it doesn't work for capture devices. You need to make some kernel changes. You can make it work, but it's not officially fully complete yet. That work is still ongoing, but you can still get it to work for the complex camera and ISP use case. So here are some references. I think that was my last slide, so we open for any questions. Cool, yeah, if there's no questions, I guess we could break early. Thank you all for attending.